Hello guys, this is Abhijit and today we'll read about electrodynamics. Okay, so the entire story of electrodynamics started with these things called as charges that we found in nature. Okay, so consider I take a charge, say a charge plus q. Okay, and say I take another charge that is also plus q. So let me name them. Say this is charge number 1 and this is charge number 2. So the entire thing is that this charge number 1 pushes the charge number 2 towards the right, okay, with a particular force. In turn, the charge number 2 also pushes the charge number 1 towards the left with same amount of force. I mean the magnitude is same and it pushes towards the left. So this is force on say charge 2 given by charge 1, and this is force, okay, that is towards the left given on charge 1 by the charge 2. So this is just labeling. Okay, so this vector symbol that I'm giving is very crucial here. Now why am I giving vector symbol? So this is the story, this is the starting of the story. But before we continue, I want to say something about forces, why they are vectors, and what do you mean by components, because it is going to help us a lot in understanding electric field and its components and solve problems. So let me give you a slight difference between scalars and vectors first. So remember, you read about scalars. Okay, so the best example of a scalar is mass. Okay, so what is scalar? So in brief, I want to say a scalar is a quantity that can add just like numbers. For example, mass. You see, mass can add just like we add integer numbers. That is 1 plus 1 is 2, or 2 plus 3 is 5, and something like that. So if you have a mass, okay, say the first mass is 1 kilo, and if you attach with the gum with this mass just another block, say of mass 2 kg, then you say that the total mass of this object, this new object, is 3 kg. You see, the addition is just like adding numbers. Okay, so scalars are just like numbers. But on the other hand, the vectors, okay, these are not so easy. Vectors does not add like numbers. Okay, vectors, they just do not add like numbers. Let me give you an example to convince you. So consider a floor. Say this is a floor. Okay, so on this floor, say I have a particular ball. On this floor I have a ball. Okay, so if I push this ball upward, so if I push this ball up with a particular force F, then what will happen? The ball will travel upward. If I force this ball with a force F towards the say left, okay, then what will happen? Then the ball will try to go to left. So there are two cases. If you apply the force upward, the ball will go up. If you apply the force towards left, the ball will go towards the left. Okay, but I want to emphasize here another interesting phenomenon. So another interesting phenomenon is, consider the same ball, consider the same ball, and now what you do is, now you give a force in this direction. Say this force is F. Okay, so what is the movement of the ball? We all know that the ball is going to move in this direction. So it is clear that the ball will move in this particular direction. Okay, the ball will move in this direction. If you analyze the motion of the ball, then you find that an interesting thing happens with the ball. That interesting thing is, the ball, when it goes from A to B, say this is A and this is point B, when it goes from A to B, the ball is not only moving upwards, but the ball is also moving towards the left. So what I mean to say is, a ball moving from A to B, okay, is having two simultaneous motions. In going from A to B, the ball is not only moving upward, but the ball is also moving towards the left. This is the origin of the concept of components. So when I see that the ball is having two motions simultaneously, it is not only moving towards the left and but also toward upwards. So I say that, say if this is a particular angle theta, okay, since the ball is moving towards the left, okay, so I say that, now you see, this force F is the only force acting on the ball. Okay, please remember, this force F is the only force acting on the ball, and this force F takes the ball from A to B. But when I analyze the motion from A to B, I find that in going from A to B, the ball is simultaneously having two motions. It is having a motion towards the left and is also having a motion towards the upper direction. Agreed? So hypothetically, what I do is, I say that the force that is taking this ball towards the left is the projection of force along the x direction. So I say that F cos theta is actually responsible for the ball to move towards the left direction, and the force that is making the ball go up is F sin theta. Okay, so why I did F cos theta and F sin theta? Well, this is just to understand. I am telling myself that this force F is actually doing two work. This force F, no doubt, at a first instance, when you see that this force F is taking just the ball from A to B. But if you are clever enough, you will see that in going from A to B, the ball is having two motions. It is going upward and it is going left. These two motions, they give a resultant motion in direction from A to B. Now, to analyze the component motions, what I do is I break the force. I say that, no doubt I claim that this force is the only force. I say that a projection of this force in the lower direction is making the ball go towards the left, and a projection of this force in the y direction is making the force go towards the upward direction. So this is the meaning of components. So what is F? So F is doing two things. So F is not only making the ball go up, so the vector is just a representation. Vector is just a representation, nothing special. So this force F, okay, this force F can be written as F cos theta. So what is F cos theta? F cos theta is the component of force that is making the ball go towards the left. So I say that there is an x motion towards the x direction. Okay, so if I take this as my x and say the upward as my y, then I say that F cos theta is acting in x direction, and the F sin theta is acting in the upward direction or in the y direction. Just to specify the direction, what I do is I place a symbol y cap. Okay, so there is nothing special about this particular formula. It is just a representation. By representation, I mean this formula is saying that this particular force that is taking the object from A to B, it is actually making the ball undergo two motions simultaneously. One motion is towards the left. Now if the ball is moving towards the left, there must be some force, and that force we name it as F cos theta, and the ball is also moving in the upward direction, and the part of force responsible for the ball to move in the upward direction is F. sine theta. So this is like we are breaking a understanding, we're trying to break an understanding into two. So what I'm trying to say here is that the motion of a ball in this um, okay, so what I'm trying to say here is that a motion of a ball along this direction, okay, the motion of the ball along this direction. Now I am trying to understand this motion using two other motion, because when the ball is going from A to B, okay, so the ball has not only reached the point C in the upward direction, but the ball has also reached the point D in the lower direction. Okay, so this is the important thing. So what I'm doing is I'm breaking a true trajectory A to B into two hypothetical motions. One motion is along the left and another motion is along the upward side. And I say that the left motion is caused due to a particular force F cos theta, which is nothing but the component of this particular force taking my ball from A to B. And the force which is responsible for the upward motion is F sine theta, which is nothing but the component of this force along the y direction or the upward direction. So this is the whole thing. This was just to make you understand what what is the concept of vectors. Okay, it is nothing but the component. So when we break a component, so when we break a vector component, it's all about we are trying to understand that particular situation by using two hypothetical situations, and both the hypothetical situations are due to two other hypothetical forces, which are F cos theta and F sine theta. This is just a way of understanding. This is just a way of understanding. So why are we doing this particular thing? Because you see, the force that a charge exerts on another charge is a vector quantity. Okay, and they add like vectors. For example, consider, so in the past, just before that, we saw how to break one force into two hypothetical force. Okay, we learned that just now, how to break one force into two hypothetical force, but we didn't learn anything about the addition. I told you addition of vectors is not simple, it's complicated. So now we'll learn about the addition. So consider a ball again. Okay, if two forces act on the ball, consider an force in the upward direction, that force is F1, and say force in the, say, towards the right, say this force is F2. So now a ball is acted upon by two forces instead of one. So I'm not considering one force, I'm considering a ball acted upon by two forces. So what is force F1 is trying to do? Force F1 is trying to take the ball up, and force F2 is trying to take the ball towards the right. Can you tell me what is the final motion of the ball? I mean, how the ball is going to move? The ball is going to move somewhat in this direction. It is very obvious, because F1 and F2 both are acting simultaneously. Okay, so the motion of the ball, that is the final resultant motion of the ball, is in this particular direction. It's quite amazing. Okay, so force, they do not only have a magnitude, but the direction of force actually matters. Why I'm giving this example, see, when you add mass, say in scalar, you saw that when you add m1 plus m2, you just add them like numbers. But here I cannot just add f1 plus f2. Oh, this is wrong. So when I say F1 plus F2, if I say that there is a force of 10 Newton, that is F1, and say F2 is 20 Newton, then it would be wrong to say F, which is F1 plus F2, is 30 Newton, that is 10 plus 20. So this is absolutely wrong and ridiculous. Okay, because this is not what is happening. This is not what it is happening. So the question is how to add these forces. So the question is how to add the forces. You see, the resultant force F can be said that this resultant force is caused due to two forces. One is F1, which is acting in the y direction, and another is F2, which is acting in the right direction, or which is acting towards the right. So this particular force is the final force, and this final force and the final direction is caused due to F1 and F2. So how to find what is Fr? Can you guess? The Fr will be just like the Pythagoras theorem formula, because the angle between F1 and F2 is, since the angle between F1 and F2 is 90 degree, so I say that the resultant force is root over of, okay, F1 square and F2 square. Okay, now you would ask, now you would surely ask, how the hell I know that Pythagoras theorem is going to help me out in carrying out the calculation? How do I know? Well, there is a subtle reason, and there is an amazing reason. The reason is the vector follows the geometry. Vector follows, usually if you're drawing vectors on a paper, then the vector will follow 2D geometry. Okay, so I'll explain about this more on the scalars and vectors video, but for now you just remember that in this particular example the Pythagoras theorem is gonna help, because F1 and F2 are both at 90 degree. There is another particular vector formula that says that if you have a ball, okay, and the ball is acted upon by two forces, say the force is F2 and the direction of force F1 is this. Can you guess in which direction the resultant F will be? Obviously somewhere like this. So this is my Fr. Now can you tell me what Fr is gonna look? So Fr will follow this geometry, that the magnitude, by magnitude I mean the value of the resultant force is actually equals to, okay, root over of F1 square, and that is an F2 square, but the catch is there will be an extra term, that is 2 F1 F2 cos theta, 2 F1 F2 cos theta. Now you would ask, why the extra term and what is this theta? Let me clear what is theta. Theta is the angle between F1 and F2. Theta is the angle between F1 and F2. So this extra term 2 F1 and F2 comes when the angle between two forces theta. Just take it for granted. Just take it for granted. This is how the vectors work, and this is how vector addition works. So scalars, they add like numbers, and vectors, they follow the geometry. It's very easy to see why vectors follow geometry, that I'll discuss later on. So now that we have understood that our force, they behave like this, so now it's time to learn about electric field. You see, consider a charge plus q. Okay, consider a charge plus q. If there is a charge here, if there is any positive charge here, then the direction in which this positive charge is going to experience force is given by this. This is the direction, so it pushes it in this direction. Now it pushes it with the force F, with the force F. Now we defined a quantity, electric field. We defined this electric field quantity just for our convenience, just to get rid of writing too much Q's, okay, or else there is not much difference between electric field and force. In terms of unit they are different, but in terms of action, in terms of using them, the use of them in solving problems, they're not different. So electric field is defined as the force exerted on a unit charge, okay, so force exerted on a unit charge. So what is q? This q is this q. So if I place any q here, then the force exerted on this charge due to plus q, so let me write this plus q as capital, okay, so you can understand there is no role of plus q. The plus q is here, the plus q is encoded inside the force, and this q is this q that we are using to test. So if you divide the total force by q, obviously you will get what? Force per unit charge. You'll get force per unit charge. Okay, why is that per unit charge? It's very easy to see. It's very easy to see. For example, say there is a force of 10 Newton. Okay, so consider there is a plus q charge. Okay, this plus q charge is pushing this small plus q with a force 10 Newton. So say this small plus q is 2 coulomb. I'm not writing the unit, so let me write, okay, let me write 2 coulomb. So what is the force? What is the test charge? The test charge is actually 2 coulomb. So a plus q charge, okay, so a plus q charge is pushing this particular charge plus q with a force 10 Newton, and if I divide 10 Newton by the test charge 2q, what do I get? I get 5 Newton per coulomb. 5 Newton per coulomb. This number actually tells me the strength. So this number actually tells me the strength of plus q. So what is plus q? Plus q is such a charge which can push any 1 coulomb of charge or a unit charge with a 5 Newton force. Agreed? So electric field is a characteristic of the source charge. Electric field is a characteristic of the source charge. So this is understood? Okay. So question is, what is the actual value of E? So what is the actual value? By actual value I mean, what is E and how do we calculate this force? So when I said that 10 Newton, this is the force, how do I calculate 10 Newton? Okay, that we'll see next. Okay, so what I'll do now is till now we read that there is a plus q charge. Okay, there is a plus q charge, and this plus q charge pushes any object radially outward. So if there is another plus q charge here, okay, then the push will be in this direction. Similarly, if there is a plus q charge here, then the push will be in this direction. Similarly, if you go on putting test charges all around plus q, it was found that this particular plus q charge was pushing everything in the radial direction. It pushes everything in the radial direction. So this is pushed this side, this is pushed side. Okay. So once I know that any electric field can be represented, okay, by lines. So what have I done here? I have just, these lines just represent in which direction the field is acting. So if you place a charge here, then the field is acting in this direction. If you place a charge here, then the field is acting along this direction. And if you place a charge here, the field is acting along this direction. Agreed? Agreed. Now we have two things at hand. Try to understand. The first thing is number of lines. And the second thing we have is lines per unit area. Okay. So let us discuss these two things. So one is number of lines and second is lines per unit area. So let us discuss number of lines. So now I know that my charges, they give electric field line radially outward. So what I plan is, I plan to use these lines to represent the strength of the force. Okay. So what I meant to say, so I said that if I draw here, how many lines have I drawn? 1 2 3 4 5 6 7 8. So I have drawn 8 lines. So my plan is, if I use 8 lines for a plus q charge, okay, then to represent a charge whose value is twice 2q. So what is the force that will be created by plus q charge? Obviously the force will be more. Okay. So to diagrammatically represent, please try to understand, we are trying to represent the force diagrammatically without numbers. Now to diagrammatically represent that 2q is going to produce more force than plus q, what I do is I double the lines. So instead of 8 lines, I plan to draw 16 lines. Okay. So consider I draw total 16 lines. I don't know how many I'm drawing. Okay. So just take it that I have drawn here about 16 lines. Okay. So I claim that these lines, they diagrammatically represent who is stronger. Okay. So the number of lines can represent the quantity who is strong. So obviously someone who has more number of lines is more strong and the charge is more. But there is one more thing. We have a thing called as electric field, don't forget that. And these number of lines are representing electric field. But the problem is, can I use this total number of lines to represent electric field? So can I use total number of lines to represent the electric field? Okay. So when I use, so if it is true, you see, if I say that total number of lines can represent electric field, then it must satisfy all the things that the electric field satisfies. So let us try to understand what are the things that electric field satisfy. One, this, the most important thing about the electric field is it decreases as we go outward. So what is the most important thing about electric field? The most important thing about the electric field is it decreases as we go far away. So this was experimentally observed. So can I say that the number of lines is gonna represent electric field? The answer is no, because the total number of lines is same whether you are near or far. For example, consider the example of plus q charge. Okay, so this is a point charge. You see, total number of lines is 8. So if you calculate here the total number of lines, they are 8. If you calculate here the total number of lines, they are 8. Hence, total number of lines cannot represent electric field, because the geometry to represent electric field, that geometry must also decrease with distance. So we have a problem. So the question is, what geometry can represent electric field? The geometry that can represent electric field is lines per unit area. Okay, so let us try to understand this. Look at this diagram. If I consider a unit area, say this is a unit area, assume. So this is drawn on a sphere. Okay, so because the equipotential surfaces that I'll discuss later on is sphere, so consider this particular unit area that I have drawn here. I'm giving color to it, okay, green one. This is drawn on a sphere. Okay, please, this is drawn on a sphere. So this unit area here, if I take it to here, I mean if I take this unit area away from it, okay, so a remarkable thing happens, that number of lines when I was near, number of lines per unit area when I was near, here the number of lines is 3. So 3 lines per unit area. As I go far away, the number of lines per unit area is 1. Agreed? So this is a quantity that is decreasing with distance. So lines per unit area is a geometrical quantity that is decreasing with distance, satisfying one of the property of electric field. Hence, the real hero here who can represent electric field is number of lines per unit area. Number of lines per unit area can represent my electric field. Agreed? Now that we have understood that number of lines can represent electric field, let us try to do some more things. Before I continue, let me give you the technical names. Okay, the technical names behind these quantities that I just defined here. Okay, so number of lines, the technical names for total number of lines is called flux. Okay, and the technical name for lines per unit area that represents the electric field is called as flux density. It's called, this is just big names, even if you don't remember, it's okay. It's all about understanding the fact that why we used the lines in the first place. We used the lines in the first place to diagrammatically represent an electric field. Agreed? But then we found that we cannot represent total number of lines to represent the electric field, because electric field has a property that as we go far away, it decreases. So number of lines cannot represent electric field. Then we tried to find what geometrical quantity can actually depict an electric field. Then we found another geometrical quantity, that is lines per unit area, that I explained here, and successfully we saw that lines per unit area decreases as we go far away, because if I keep a unit area very close to the charge, I get more number of lines passing through it. If I take the unit area away from the charge, I get less number of lines passing through it. So number of lines per unit area is decreasing as I go far away. Agreed? Hence, lines per unit area has the power to represent the electric field. Now some more interesting stuff coming up. Please understand that this is not circle, these are actually sphere, because we are talking of electric point charges in space, and these point charges, they have these electric field lines. Look, I'm drawing electric field lines. These electric field lines, they come out in all direction. In all direction means I'm actually talking 3D, I'm not talking 2D. On the board you can see everything is 2D, but actually I'm talking of 3D. So if you have a electric charge on space, then the total number of lines is 3D. I mean, the total number of lines are coming out in all direction. This type of electric field lines are called as diverging electric field. It is called as what? Diverging electric field. So why it is called diverging electric field? Because the electric fields are starting from point, that is the charge, and it is going till infinity, that is it diverges. So diverging electric field. Now why are we studying this? We have done so much of things here, and what are we trying to do here? Well, we are trying to find a mathematical formula. I mean, I want you to prove the mathematical formula of the force. You remember what force is? The Coulomb's law. Okay, so let us try to understand this force or the electric field. Let us try to write what the electric field is. So the electric field is a quantity whose value is proportional to the charge. Would you agree? Why the value is proportional to charge? If I take a less charge like plus q, the number of lines are less, and if I take a more charge, if I take a bigger charge like plus 2q, the number of lines is more. So electric field is directly proportional to the q, and electric field is inversely proportional to the area that it covers, or it is inversely proportional to 4 pi r square. So what is this 4 pi r square, and why I have written it down? Please see that 4 pi r square is nothing but surface area of the spheres. Okay, so consider the smallest sphere. For the smallest sphere here, the surface area is 4 pi r square. The value of r is less, and the value of electric field is more. So when we have a smaller surface area, the value of electric field on the equipotential surface, this is called equipotential surface, because the value of electric field on this sphere will be same, because it is at a distance r from q. Okay, all the surface on the sphere are at a same distance. If I go to a bigger sphere, when I say I'm going to a bigger sphere, I'm going to a sphere with surface area 4 pi, say r dash square. By r dash I mean I went to another big sphere. Here the electric field is less, because if I take a unit area on this sphere, the number of lines passing through unit area of this surface is 2, and here if I draw the unit area, the number of lines passing the unit area is 3. If I go farther away, if I go to another bigger sphere whose area is 4 pi r square, okay, if I draw a unit area, I find that unit area is drawn on the sphere. I find that the number of lines passing through this unit area is 1. It means the value of electric field is somehow depending upon the increase or decrease of the surface area of the spheres, where the spheres are equipotential surfaces. If I'm taking a smaller sphere, it means I am very near to the charge, hence my electric field is going to be high. So smaller is the area of the sphere, greater is the electric field. So can I write this as this? So this electric field is some behaving as if, no doubt the electric field is proportional to charge, no doubt if I take a more charge, then the electric field is going to be more, but somehow this electric field is also inversely proportional to the surface area of the equipotential surfaces. Surface area of equipotential surfaces. Okay. So forget this equipotential word, you just remember surface area of the spheres. Okay, so these are nothing but surface area of the spheres. Okay, so why I'm saying you sphere, because on a particular sphere the electric field is constant. You see, because any point on the sphere, for example take the bigger sphere, all the point on the bigger sphere are at same distance from plus q, and hence I claim that on all these points the electric field must be same. Okay, so what did we learn? We learned the formula that the electric field is directly proportional to charge, which is true. If I take more charge, more is my electric field, and the electric field decreases as I go away. So when I go away, I'm moving from smaller spheres to the larger spheres. So the quantity upon which the electric field is depending inversely proportional is the area of the sphere. The bigger is the area of the sphere, it means I am larger distance away from the charge and my electric field is less. Agreed? So this makes us come very near to the formula E is equals to Q by 4 pi r square, but we have not put any proportionality constant here. So let us do it. So if I write this formula as E equals to, so this is a vector. Oh, I'll tell you why it's a vector. It's a force, so it's a vector. Some constant k into q divided by 4 pi r square. Agreed? Now the idea is, what is this k? What is this k? You see, this k turns out to be 1 by epsilon naught. Okay, let me tell you why. The reason is, the electric field here, okay, is a field in space, and it was found that the value of the electric field will decrease if you take a charge and put the charge inside a wall. So we have two conditions here. So if you take a charge and put the charge in free space, then electric field is more. Okay. And if you take the same charge and put this charge inside a concrete wall or inside a solid box, then the electric field produced by this charge inside the box is less. Okay. Unlike gravity, this is the only special case for electric field. You see, gravity is produced by mass. Whether you put this mass in space or whether you put this mass in a particular enclosure, it doesn't matter. Hence the value of value of the force due to gravity is same, and the proportionality constant g is called universal proportional constant because it does not change. But the problem here is, if you put the charge in free space, the electric field is larger. If you put the charge inside a closed box and the box is filled with some material, say brick or cotton or whatever, then the electric field is less. So apart from q, that is the charge, and apart from 4 pi epsilon naught, there is one more factor that is hurting our electric field. The factor is something called as the nature of material. So the nature of material is also a factor that is responsible for the value of electric field. For the vacuum, the value of the material value, we have given a value of epsilon naught to vacuum. Okay, and any material has a value epsilon, and any material will have epsilon greater than epsilon naught because E is less than electric field in vacuum. So let me write electric field in vacuum as E naught. Okay, so in this case the formula will become 1 by epsilon, and because of this epsilon, the value of this field, which is E, is less. The value of this is less because the value of epsilon is more. And here okay, it is 1 by epsilon naught, and the value of E naught is large. The value of E naught is large. So these things, these constants E naught, these are called as the permittivity constants. Okay, there is a special name for that. Now what is this E naught? This is something related to dielectric. So when I teach dielectric, so I'll tell you the origin of epsilon and epsilon naught. So now you just think of epsilon and epsilon naught are the values that are given to the surrounding inside which we are keeping the charge. If we are keeping the charge in vacuum, then we give a number epsilon naught to the surrounding, and if we put the charge inside some concrete wall or inside some material, we give a value of epsilon to that material or the surrounding. If the surrounding is vacuum, the electric field is more. If the surrounding is anything other than vacuum, then the electric field is less. That is why the epsilon or epsilon naught is in the denominator, because the electric field value is inversely proportional to the surrounding. Agreed? So what information does epsilon and epsilon naught contain? They contain the information of the surrounding of electric field. They contain the information of surrounding of electric field. So hence, after so many things, we have reached the conclusion. So our conclusion is the following. 1. Electric field lines or the electric field can be represented in the form of lines. but the real thing that describes the electric field is actually line density. Okay, this is the real quantity that can describe the electric field. Second, electric field is more if the charge is more. Electric field is less if we go to the bigger sphere. I mean, when we are going to the bigger sphere, see, when we are going to the bigger sphere, the value of R is large, and as a result of which the value of the surface area is also large. So when we go to bigger sphere, electric field is less, and if we put the electric field, if we put this particular charge in a surrounding, then that is a particular number given to the surrounding that also dictates the value of electric field. That number is either epsilon for any other surrounding and epsilon naught for vacuum. So what is the formula? So usually in books you find the formula is 1 by 4 pi epsilon naught, okay, q by r square. Here I have given you an alternate description of electric field just to make you aware that there is a term 4 pi r square which is related to the surface area of sphere. Okay, this is very important actually. People only see the value of r square and they don't understand the importance of r square. Some people argue why there is an r square. Okay, so the reason there is an r square is because we are dealing with 3D, and in 3D the lines are, the value of the lines are decreasing as per the sphere. If you take it 2D, then you should consider circles. Let me give an example. So remember centripetal force in your first year. Centripetal force is actually given by m v square by r. So you see the r in the centripetal force is because the centripetal force, when you study it, you actually study in 2D. There is nothing called as 3D centripetal force. Centripetal force is always 2D. Hence you have a r term. And to deal with centripetal force, you either take 2D ellipses or you take 2D circles. So what do centripetal force do? It makes motion. So if there is an object here and if there is a another object here, okay, so under the influence of the sun, so let me write, under the influence of the sun, the earth is moving in an elliptical path, and this elliptical path is 2D. If you take a stone and if you rotate the stone using a thread in a circular path, this is also 2D, and the force hence is proportional to the r. There is no r squared term. Agreed? So the r squared term only comes when you are working in 3D, because when you are working in 3D, the force decreases as we go to higher and higher sphere. When we work in 2D, the force decreases when you go to higher and higher circles. The force decreases when you go to higher and higher circles. Agreed? So that is conclusion number 2. Let me cut this part. So what is conclusion number 3? So the conclusion number 3 is the electric field, if I take the 4 pi r square term here, 4 pi, if I take the 4 pi r square term here, then I am only left with q by epsilon naught. Agreed? I am only left with q by epsilon naught. This mathematical term is called as flux. this mathematical term is called as flux. But you would question me that you defined flux as number of lines. So why is that flux, which represented nothing but number of lines, okay, suddenly takes a mathematical representation which is electric field multiplied with area? Why is that? Okay, so let us try to understand. So till now I gave you a geometrical representation of flux, just a geometrical representation of flux. Now I will teach you the mathematical represent of flux that you see here, and you are getting confused. Okay, let us try to understand. If you look at this formula carefully, okay, and if you look at the geometry carefully, can you return to our previous discussion, the one we started, and I said that number of lines is directly proportional to charge. Why? When I took plus q charge, I drew only 8 lines. In second example, when I took plus 2q charge, that is double of the charge above, then I told you that I will draw total 16 lines, because these lines will tell me where the charge is more. So number of lines not only tell me where the charge is more, but number of lines, they also tell me whose electric field is more. So the truth is, so number of lines actually is proportional to charge. So number of lines is proportional to charge. Agreed? Because more is the charge, more I should draw the number of lines. That was the assumption. Okay, and why did I draw number of lines? The only reason I draw this number of lines is to understand. If I draw more number of lines, I know that there is a charge inside which is larger. If I draw small number of lines, I know there is a charge inside which is less. Now can you tell me, from comparing to this particular formula, which mathematical term is proportional to q? Since epsilon is a constant, just forget it. If you look at this formula carefully, the only mathematical term proportional to q is E dot 4 pi r square. This is the only term which is proportional to q if I rewrite the formula. Hence, I am bound to represent this mathematical quantity E dot 4 pi r square as number of lines. It's quite logical. Everything is intuitive. Everything is intuitive. So E dot area is proportional to q, and E dot area is called as flux, because flux is number of lines, and number of lines, they depend upon charge, and E dot area depends upon charge. Hence E dot area is proportional to flux. It's very logical. Now that we have defined flux, let me go one step further, and so from here we will learn something called as Gauss law. If we go to the fourth conclusion, the Gauss says that the multiplication of electric field with area is the mathematical object which is describing number of lines whose technical term is the flux. Okay, so forget the technical term, or remember, doesn't matter. And this number of lines was in turn proportional to q, because in the starting we took the number of lines to understand whose charge is more. That was the initial idea. So this in concrete mathematical style is written as integration E dot ds. So this is nothing but the multiplication of electric field with area. So why did I use a surface integration? So it is used when, see, when you multiply E dot A, you are assuming E and A are constant. But if E is changing with area, I mean if the value of E or the direction of E is changing with area, then you need to integrate it to find the total flux. This is a very simple idea. It's a very simple idea. So so integration E dot ds is equals to q. Okay, let me not write equals to, let me say it is proportional to q, and this can be in turn written with a proportionality constant, which is my epsilon naught, that is E dot ds is equals to q by epsilon naught. So this is the famous Gauss law. So this is the famous Gauss law. In the next lecture, we will look at some of the application of Gauss law. We'll look at the power of Gauss law. Okay, so how powerful is this formula? We'll try to look out. Okay, thank you for listening. Bye bye.